Hi students, in this video we're going to talk about the length of arcs. You should have seen arc length in Calculus 2. We know this formula. The length of an arc is really just the speed integrated from some start point to some end point for a continuous function. In this case, we have a vector function, and the formula is written for three components. And this is assuming that we have a vector function that has the following components: r of t is equal to, then we just have an f of t component, a g of t component, and an h of t component. If there's a vector that has two components, we just don't need the h of t, but the formula is otherwise the same. So for our first example, we have to find the length of this arc, and we're going to graph the arc in GeoGebra. I've already graphed this function. I remember to graph a function in GeoGebra is some variable equals, and then for a curve, we actually type the word curve. We put in the parameters, the parameter variable, the start point, and the end point. So what we get is something that is like a parabola. We'll talk about how we can express this curve in terms of x and y in class, but this is effectively what it looks like. And from t equals 0 to 4, if you can, let's put in the point, we'll say a is going to equal, so we know we're starting at the origin for 0, 0, but then we're going to say a is equal to r of 4, and that point 1664. So we're starting, like, even though, so our x's don't stop at 4, our x's are going to actually stop at 16. And so we see, like, up here is really the length of the arc that we're finding. It stops right there. So that length is what we're actually finding. So all we need is the derivative to calculate the magnitude of the derivative and see what function we get when we integrate. So r prime, and again, keep good notation. So r prime is going to equal 2t, and the second component has a derivative that is 3t squared. And the magnitude of r prime is going to equal the square root of 2t squared plus 3t squared, so quantity squared. And that's going to give us the square root of 4t squared plus 9t to the fourth. And from there, we can actually factor out a t squared. So we get t squared times 4 plus 9t squared. And the square root of t squared is going to allow us to take a t out. So we get the square root of, we get t times the square root of 4 plus 9t squared. And we want to find this length on the interval 0 to 4. So we have this integral from 0 to 4, and our speed simplified to be t, and we're going to rewrite 4 plus 9t squared to be 4 plus 9t squared, with the square root we're going to rewrite to be 4 plus 9t squared to the 1/2 power dt. So this is a problem that requires u substitution. So if our u equals 4 plus 9t squared, its derivative is 18t dt. And what we need to replace, we'll underline, is a t dt. So that would mean that 1/18th du is equal to t dt. And we would like to express our integral in terms of u's instead of t's. So our limits for our integral. So if t is some number from 0 to 4, Our u's are going to be, remember, to get your new limits, you substitute these t values back in to t over here. So we're going to get 4 plus 0, which is 4. And if we substitute in 4, we're going to get 4 squared is 16 times 9 is 144 plus 4 is 148. Cool. So what we actually get is 1/18th of some integral from 4 to 148. And again, the 1/18th replaces the t dt, but since it's a constant, we put it in the front. And then we get u to the 1/2 du. Now from here, we're just applying basic rules for integration. So we're going to get 1/18th u to the 3. Oh, why did I do that? So we're going to get 1/18th u to the 3/2 divided by 3/2. So that means that we actually multiply by 2/3. And we need to evaluate that from 4 to 148. So if we simplify a bit, we're going to get 2 over 54, or 1/27th of u to the 3/2. And we want to evaluate that from 4 to 148. So all this is going to give us is the square root. So we can take the 127th, and we're just going to have 148 to the 3/2 minus 4 to the 3/2. And 4 to the 3/2 is, the square root of 4 is 2, so 2 cubed is 8. 148 is not a perfect square, and does it? So that's 2 times 74, 4 times 37. So it is, let's see, the square root of 148 is equal to the square root of 4 times the square root of 37. So that's 2 root 37. It's not a great number. Generally, arc length isn't. So we're going to get 1/27th of 2 square root 37 cubed. Oh, this is all in parentheses. Minus 8. And you can check that on a calculator. You can throw this into Desmos as an integral, and it gives you some value. And you can check the value against that. But sometimes these don't work out cleanly. That's perfectly fine. But again, all that number represents is the length of this arc, the curved arc, not the actual line. So sometimes they work out cleanly, nice round numbers. Sometimes they do not. But the integration is what is important. For our second example, we have this function that has 3 components. We have e to the t sine t, e to the t cosine t, and e to the t. So it seems like it might be a beast of a problem. Let's see what we get. So our first derivative is, all right, so product rule for the first component, that's going to be e to the t, because the derivative of e to the t is e to the t times sine t, plus the derivative of e to the t, I'm sorry, the derivative of sine t is cosine t, so e to the t cosine t, comma, and then the derivative of e to the t is e to the t, so times cosine t, plus the derivative of cosine t is negative sine, so we're going to actually make this a minus. So minus sine t e to the t, which is the same as e to the t sine t. And the derivative of e to the t for the 4th time is e to the t. Cool. So the magnitude of r prime of t is going to equal, ooh man, this is ugly. So it's going to be, see how we can simplify this. So it's going to give us the square root of e to the t sine t plus e to the t cosine t squared plus e to the t cosine t minus sine, or we'll say e to the t sine t as well. So minus e to the t sine t squared plus e to the t squared. Let's see what we get. This might be something we throw into a calculator because it could just get too ugly. But some of this stuff we can do by ourselves. So for the first term, we're going to get for this first square, we're going to get e to the 2t sine squared t plus, so then we can write this out here. So if we have like e to the t plus sine t plus, I'm sorry, hold on a moment. If we had e to the t sine t plus e to the t cosine t multiplied by itself, what we would get is, all right, so for the first term, that's going to give us e to the 2t sine squared t. And then we're going to get two terms that are e to the 2t sine t cosine t. So that's going to give us 2e to the 2t sine t cosine t plus e to the 2t cosine squared t. So what we should immediately see is that sine squared plus cosine squared equals 1. So that's something that we can get rid of. And then if we continue for the second term, it's actually going to turn quite ugly. Maybe some stuff cancels though. We'll see. So then we get plus e to the 2t cosine squared t minus 2e to the 2t sine t cosine t, and then that last term is going to give us a plus e to the 2t sine squared t. For this very last term, we're just going to get a plus e to the 2t. Really, really ugly. But fortunately, what cancels is this term, and that actually gets rid of a lot of our problems. So what we're going to see again is that cosine squared and sine squared are going to make 1. So we can group these things. We can factor out an e to the 2t from everywhere in our square root. So let's go back. So what we're going to get is the square root of, and we're taking out this e to the 2t. These terms completely cancel. We're taking out that e to the 2t, that e to the 2t, that e to the 2t, and that one. We're factoring all that thing out. So we're going to get e to the 2t, and that's going to leave us with sine squared t plus cosine squared t once for this one and for that one. But then we're going to also have plus cosine squared t plus sine squared t because of this cosine squared and this sine squared. And then if we factor out e to the 2t from that term, we're going to have plus 1 left over. So it's actually going to work out quite nicely. So we end up with the square root of, so sine squared plus cosine squared, that's 1, and that's 1. So that's really just 1 plus 1 plus 1, which is 3. And the square root, let's write this over here. The square root of e to the 2t is just e to the t. So what we end up with is e to the t times the square root of 3. So that's what we want to integrate. A lot of work to get to that though, right? So the integral from 0 to the ln of 2 of root 3 e to the t dt. Fortunately, e to the t is its own antiderivative. So we get root 3 e to the t evaluated from 0 to the ln of 2. And that's going to give us root 3 e to the ln 2 minus root 3 e to the 0, which e to the ln of anything is the anything, assuming the argument is valid. So e to the ln of 2 is equal to 2. So we're going to get 2 square root 3 minus 1 square root 3, which is just the square root of 3. So that's our final answer. We didn't graph the curve in GeoGebra, but it's just a curve in 3D that goes up from 0 to the ln of 2. If you put this into Desmos or GeoGebra as an integral, you would get this value. So again, a lot of our work here is algebra. The calculus was actually quite easy. This step is our calculus. All of this is our algebra. Made us angry. Third example. So if the speed actually turns out to be 1, the parameter t that we get from making an arc length function is actually always going to correspond to being the it's always going to correspond to being the arc length at that time t. If you'll indulge me for a moment, I'll erase this for example 3, but imagine that we had simply the curve r of t equals, and we're just going to do the unit circle, so cosine t, sine t, and we want to do this on the interval 0 to 2 pi. So the derivative is negative sine t cosine t, and so then the magnitude is equal to the square root of, we'll get sine squared t plus cosine squared t, which equals 1. And so the arc length is going to be the integral from 0 to 2 pi of 1 dt. So again, that magnitude was 1. And so when we integrate this, we're going to get t, because the antiderivative of 1 is t, so t evaluated from 0 to 2 pi, which is just 2 pi minus 0, which equals 2 pi. Now, what we know about, if you remember when you were first introduced to radians, is that along the unit circle, I drew a unit oval. That's not great. Let's go back. Let's see if we can draw a better circle. So if we have a circle, cool. So any point, we'll say, like this part that we've traversed on the unit circle, assuming that radius is 1, is equal to the length of the arc. So as you move around, you get the length of the arc. When we're writing an arc length function, we're just assuming some other parameter other than t is our input parameter. So if we went back and made an arc length function where we evaluated from 0 to so we're going to change this up a bit. So if we evaluated from 0 to t, and we made this like du, for instance, we're going to get the same function. But that's going to equal, this time is going to equal u evaluated from 0 to t. And it's still an arc length function, but now t can be whatever value we want. So we could say t could be from 0 to pi over 2, from 0 to 2 pi, but all we're going to get is always the value of t. So when the arc length when the speed is 1, the arc length, we can make a function where the parameter is always going to be a function of the arc length. So for this example, we want to determine if the arc length is a parameter of the curve. And all it means is that the magnitude of the derivative is 1. So let's see what we get. So we get r prime of t is equal to, all right, so all of these are 1 over square root 3 t. So all of our derivatives are 1 over root 3. So 1 over root 3, 1 over root 3, and 1 over root 3. So clearly the magnitude of this is the square root of 1/3 plus 1/3 plus 1/3. And you know 3/3 is going to equal 1. So the square root of 1 is 1. So because we got a magnitude of 1, we know that the arc length can be a parameter of this curve, which again, all that means is that for every value of t, when you substitute in t, what you get is the arc length. So imagine we have this arc length function s of t, and it equals the integral, and we'll say from 0 to t of this function du. So we're going to get some function, and that's just going to equal t. So whatever value of t we substitute in, that's going to be the arc length for this function. For example, 4 is going to actually turn out that it's not a parameter, but we'll see why. Spoilers. So we're doing the exact same thing, but if the curve is not, if the arc length is not a parameter of the curve, we want to write a function that we can have the arc length as a parameter of the curve. So our derivative is going to be 1, 2, and 6. And the magnitude of the speed then is going to be the square root of 1 plus 4 plus 36, which is the square root of 41. Cool. So 41 clearly not equal to 1. So what we can say is the arc length at any point is not a parameter of the curve. So arc length is not a parameter of the curve. Now, again, all it means is that when you substitute in t, you're not going to get the arc length at that point. You're going to get some multiple of the arc length. So to get around that, then we can still integrate this though. So we got that our magnitude was root 41. So say we wanted to write an arc length function. So s of t, s is for arc length, is the integral from 0 to t. And we want to take this value root 41 du. Now that's just going to give us root 41 u evaluated from 0 to our value t. So that's just going to give us root 41 t. Now our parameters up here are written in terms of t. So if we take this function s, and we don't have to have, we can say s of t or we can say s. So if s is equal to root 41t, to properly parameterize this so that we get a parameter that's going that we would get a speed of 1 when we take the derivative, we could just say, well, t is equal to s divided by the square root of 41. So now if we write this separate function, we'll call it r1 of t, we'll say it's r1 of t. So we'll actually put it in terms of s. So like r1 of s is just going to equal, and we're going to replace t with this s over root 41. So s over root 41 plus 1, 2s over root 41 minus 3, and 6s over root 41. And so if we found this derivative r1 prime of s, that's going to be, now s is our variable, so we're going to get 1 over square root 41, 2 over square root 41, and 6 over square root 41. Where now if we find the magnitude of this vector, we're going to get 1, hold on a moment, that should be a square root. We're going to get the square root of, all right, 1 over square root 41 squared is 1 over 41. 2 over square root 41 squared is going to be 4 over 41. And 6 over root 41 squared is going to be 36 over 41. And so it's going to be 41 over 41. It's the square root of 1. So this function allows us to make the arc length be a parameter. So what that means is that if you wanted to find the length of the curve, if you took this function and just substitute in some value of s, what you would get is the arc length of that curve. But you have to like find the derivative and anti-derivative subsequently first. Kind of tricky. So last thing is, we can also do this for polar coordinates. So in polar coordinates, the arc length has this formula. It's almost the same thing. We have the integral from a to b of the square root of the function squared plus its derivative squared, and r is just some function of theta. And we want to find the length of this arc, 4 plus 4 cosine theta, and we'll say on the interval from 0 to 2 pi. All right, so we will review polar coordinates in class so we can remember how to read the curve. For now, we're going to plot this in GeoGebra. So let's hop back. It's 4 plus 4 cosine theta. So first, let's put this in polar coordinates. General, so coordinates, nope, what do I want to do? How do I want to do this? I saw it earlier. Nope. Where is it? Grid type. Oh yeah, grid type. So we want it in polar. So let's delete both of these curves. And we want the function to be r equals, what was it? 4 plus 4 cosine theta. So 4 plus 4, and function wise we get cosine, and do we have a theta? Whew. Oh, it gives us the Greek letters and theta. Is it gonna show up? Oh, hold on, I want to be in polar coordinates though. Grid type polar. Gotta type it over. So we just do 4 plus 4 cosine and theta. Maybe we'll zoom in that far. So, all right, let's change our labels. Nope. We want to change the. All right, let's screenshot. Let me take a screenshot of this so we can talk about it in like just the notes app or something. This is just be a quick review of polar coordinates. Actually, I can just mark this up. So, all right, in polar coordinates, all right, so this curve is r. This curve is r equals 4 plus 4 cosine theta. So let's track some values of theta. So again, theta is going to be in radians. So when theta equals 0 radians, we're going to get 4 plus, the cosine of 0 is 1, so we're going to get 4 plus 4, and that equals 8. So that's why we start here at theta equals 0. Now another one that we can track is theta equals pi over 2. So we know the cosine pi over 2 is 0. So we're going to get, when theta is pi over 2, we're going to get 4 plus the cosine of pi over 2 is 0. So 0 times 4 is 0. So that's going to give us 4. So here, this is theta equals pi over 2. And what we're doing is, imagine you took an angle and you sweep it up. So from 0 to 2 pi is going to get us to here. From pi over 2, and I'll trace this in red. So from pi over 2 to pi is going to get us back to the origin. So this part of the curve is from 0 to pi. This part of the curve that I'm going to trace in green is from pi to pi over, from pi to 2 pi. From here, this is going to be at this dot here, we're going to have 3 pi over 2. So what we can do is integrate from 0 to pi and just double the result to get our arc length. So that's what we're going to do. Let's hop back over to the notes. So what we're going to do instead of 0 to pi is just do 0 to 2 pi is from 0 to pi. We're done with that and we can delete it. Cool. So according to our formula, we would get arc length is equal to the integral from 0 to pi of the square root of, so r squared is just going to be 4 plus 4 cosine theta squared plus the derivative squared. So r prime of theta is equal to negative 4 sine theta. So then negative 4 sine theta squared. So when we multiply this out, what we're going to get is the integral from 0 to pi of the square root of, all right, so if we multiply this out, we're going to get 16 plus 8 cosine theta plus 16 cosine squared theta plus 16 sine squared theta. And this is going to equal the integral from 0 to pi of the square root of, all right, so cosine squared plus sine squared is 1. So 16 cosine squared plus 16 sine squared is 16. So we're going to get 16 plus 16 is 32. So 32 plus 8 cosine theta. I'm sorry, I forgot d theta is at the end of this. And from here, we're going to get the integral from 0 to pi. And we can factor out a, 4. So we get 2 times the square root of 8 plus 2 cosine theta d theta. And I think this is as far as we can go without applying some slick trig identity. So from here, you would substitute this into a calculator. I'll leave it up to you to do that. Let's say we set this, like for this one, we set it up and use a calculator to evaluate. So that is going to be the end of that problem. I'm sure there's some half angle identity I'm forgetting that we can apply here, but that's not super important. It's more important that we can set up the integral. All right, so is that the last one? Yeah. All right, so that'll conclude this video. I'm sorry about that long tangent about the polar coordinate stuff. Anyway, see y'all in class.